Okay, in the name of Allah, the most gracious, the most merciful, all praise is for Allah, the Lord of all worlds, the most gracious, the most merciful, Master of the day of judgment. You alone we worship and you alone we ask for help. Guide us to the straight path, the path of those who you have blessed, not the path of those who incurred your anger, nor of those who are astray. God, be with us through today, all our sessions. Give us good health, give us wisdom and knowledge to grab all that will be presented to us. Let's make the session interactive and we get the best out of it. Amen.
Amen. Thank you very much, Ms. Mwanganga, for the wonderful prayer. Now, before we start the first session, which will be led by Dr. Benson Oyunge, and the co-chair will be Ms. Fatma Mwanganga. I would like to inform you that today is the second day of our conference, and yesterday was very successful. We had keynote speeches from different speakers, and it's also important to note that the last keynote speech that was to be given by by Dr. Ordonez was given yesterday, so it won't be given. That is in the last. If you have got the program, then that will not be taking place today. So probably we may finish early today. And after the first session, we will go to the breakout sessions, session 1 and 2. And then after the session 1 and 2, which will be led by Dr. Robert and also Dr. Engineer Joseph. Sorry, Kiburi, just Engineer Kiburi. So after that, then we'll have a short break, that is lunch break. Then we'll come back for session 3 and 4, lunch, then session 6 and 7. And in between, we'll be having keynote speeches. So allow me to invite now Dr. Benson Oyunge, who will introduce to us our keynote speaker for to begin with for this day. Thank you very much, Dr. Benson Oyunge. Dr. Benson Oyunge is a lecturer in the Department of Marine Engineering, and he is also one of of the members of SRI committee. Thank you, Dr. Benson.
Thank you very much, Dr. John Othiambo, for the welcome. And thank you very much, everyone, for finding time to come to SRI conference, the second day. So it's my honor to introduce Professor Sakaguchi, Professor Daisaku Sakaguchi from Nagasaki University. So if I was to have enough time, I'll need a lot of time to introduce Professor Sakaguchi, but because we don't have enough time, I'll just take a few minutes. So first, he is a professor of mechanical engineering and the Dean, Graduate School of Engineering at the Nagasaki University in Japan. And the second point is that he was my advising professor when I was doing my postdoctoral studies at the Nagasaki University for about 1 year. And so while in his laboratory, he gave me a very unwavering support. And I was able to catch up very fast with the studies in the lab, and we were able to publish a couple of journal papers with him and his students. Yeah, so another one is that Professor Sakaguchi, his areas of research include fluid dynamics, turbomachinery, which includes turbines, pumps, fans, and compressors. And he also does multi-objective optimization, one of the unique areas that is done in his laboratory. And another thing I want to say is he works closely with JQuat and a number of things. One of them is together with Professor Kiyasu, they are supporting the robotics competition at JQuat. And I understand most of you know that yesterday was the day for this competition, and I believe we had a successful event yesterday, courtesy of their support. Another point is Professor Sakaguchi accepts Kenyan students to his laboratory. And so currently there are 2 PhD students in his laboratory. And this is Adam and Grace. And I believe today, with Professor Sakaguchi's permission, we have Adam here. Maybe he can just rise and wave to us. Yes, thank you very much. We will have time to interact with him. And the last point is that Professor Sakaguchi works with the CFD research group at JKUAT in the School of Mechanical Engineering, whereby we work together with him in order to develop some optimization tools, which will be very beneficial to us when we design turbo machines and other related applications. So you see JKUAT and SOME working closely with Professor Sakaguchi from Nagasaki University. And we believe that this relationship will continue to grow with time, and we have very successful collaborations leading to sustainable research in a couple of fields together. So this is a short introduction about Professor Sakaguchi. And now it's my honor to welcome Professor Sakaguchi to the podium to give his keynote speech. Welcome, Sakaguchi Sensei.
Thank you, Benson. Thanks again, Benson. Very kind introduction. I'm Sakaguchi from Nagasaki University, Japan. And today my topics is so it's including the 2 parts. The first part is about the renewable energy, and the second part is the optimization technique. So recently, it's getting more important, this kind of renewable energy, especially in Africa. And you have a lot of resources, and we are very, very interested in this kind of development. And the main player is here. So solar energy and wind energy, and especially geothermal is very, very strong player in Kenya. And I'm also interested in this kind of tidal turbine. So maybe we need to combine this kind of renewable energy and mix it, and should be stable and try to manage well. And the wind turbine, maybe it's a next challenge. And in the world, the turbine size increasing. Recently, the diameter becomes more than 200 meters. And if it's rotated around 10 RPM, maybe you can calculate the tip speed of this turbine will reach to more than 100 meters per second. So it's corresponding to the 360 kilometers per hour. So extremely fast, and it should be run more than 30 years. So it's very, very severe condition. And moreover, recent topics is so near shore, the area is limited, and it's difficult to install this kind of huge turbine. So this large-scale huge turbine will go to the offshore, and of course, the depth of the sea increasing. It's going to the more than 100 meters. So that means it's difficult to install as a fixed type. So it should be floating type. Floating type wind turbine is next technology, and there are many issues, of course, but we should be develop this kind of huge turbine. And so this is the potential map in the world, and Kenya is here, not so bad. Japan around here, not so bad. And the north side of Europe and south side of Africa is very, very interesting area. So many countries face to the sea, and they can get energy from the ocean. And so when you are looking at this table, so Africa is here, so potential for the deep water is extremely high. So in Africa, we also need to develop the floating type huge scale wind turbine. So it's the next challenge in the world. And this is the power vision from Japan, and Japan is planning to develop the 10 gigawatt wind turbine, and it should be installed until 2030s. It's coming soon. So many places has already started this kind of installation, and Nagasaki is also interesting place, and it's scheduled more than 300 megawatt. So we are surrounded by sea, and this project has started already, and Japan trying to increase the size of this capacity toward the 2040, 2050, and so on. So for this development, we need human resources, we need a scientist and engineer. So for this purpose, our university trying to make special courses, and many Japanese university getting together and working with the energy companies. We are making a consortium and developing this kind of wind turbine. So this picture is coming from the west side of Nagasaki, and this is a very unique spar type wind turbine. It's a floating type. And it's already installed, and it starts generating the powers. And the tidal turbine is also interesting energy source because it's predictable. So if you have a sun and moon, you can estimate how much flow you have tomorrow, the day after tomorrow, 10 years later. So it's predictable. Normally, renewable energy is unstable, but however, this kind of tidal turbine, geothermal is also stable energy. So it's an interesting point. And if you are surrounded by sea, of course, Kenya, you have a Mombasa. So it's a very good place to develop this kind of energies. And so the density of the water is 800 times than air. So energy is very, very strong. And it has a great potentials. And normally, environmental impact is extremely low for this tidal turbine. And there are several scales of the tidal turbine there. And our university developed this kind of tidal turbine. And Benson-san developed this turbine with shroud. So this shroud, its effect as a diffuser and reduce the pressure at the inlet of the turbine, and incoming flow increase based on these pressure differences. So good design is highly required for this turbine and impellers. The difficult point is when you combine this kind of impeller and shroud, this yellow part is called shroud. Nobody knows how to design it. And today, later section, I want to talk about the objective optimizer. And this is very, very useful to develop and design this kind of new turbines. And another one is it's very, very small scale, but it's very effective. So the C is wide and difficult to search. So we need to install many devices. But however, it's very difficult to keep in the batteries, and it costs a lot when you're changing the many batteries. So in this project, the tidal turbine is attached the bottom of this smart buoy, and this design should be work well. And of course, this design is also difficult, but we are succeeded well about for this development. And so most of the renewable energy faces the unsteady boundaries. And this is an example of the tidal condition. So you know, tidal condition always changing the direction every 6 hours. And that means there is no rated speed, no rated rotational speed. So normally turbo machinery is based on this rated condition and try to improve the efficiency as much as possible. However, when you face this kind of renewable energy, no rated condition. So it should be work and it should be has a high efficiency at the highest condition and the middle condition. So the previous design technique is not useful and it's not applied for this kind of renewable energy devices design. And I want to try to explain how to do that, how to design of that. And this kind of things is many places. When you want to play with the renewable energy, you need to work with the airflow and the compressor and water flow and pumps and turbine and so on. So we need to develop this kind of turbo machinery, especially adapted to the renewable energy. And this is the example from our lab. And of course, there are more devices should be developed. There are many types of the turbo machinery there, and we need to develop. We need to find out a good design. It works very wide range and high efficiency. So I mean, so for the compressor map, so horizontal axis is a mass flow rate, and the vertical axis is a pressure ratio. It's called compressor map. And so this is the constant speed line of the impeller. And so this is the maximum efficiency point. And so when you face it with renewable energy, again, I need to say the inlet condition always changing. So this compressor should be work in a very wide range. So efficiency area should be wider and wider. So it's a new issues for the turbo machinery, and the final target, final achievement of our project is to increase, we call the I of the efficiency. I of the efficiency should be widely open, and it works well in the wide range. So I want to try to introduce my optimization system. So it's very, very powerful tool for the renewable energy development. And I combined with the neural network and the genetic algorithm. So nowadays, AI, artificial intelligence, is fundamental technologies. And however, for the engineering development, it's a little bit difficult to use. And today I want to introduce the how to modify it and how to combine with the design technique for the turbo machinery. Basically, I just want to confirm the difference of the single object and multi-objectives. So this is a single objective, and so vertical line is a single objectives, and this is the minimum problem, and horizontal line is the design vectors. So this is not so difficult. You can easily to find with a limited area and restricted area, and under the feasible region, you can find the minimum point of this design. So this is not so difficult. Nowadays, we need to fight with several objectives. So when you have more than two more objectives, so this is the two objectives, and there are many characters of the design here, and this is the original design. But when you change in the parameter, you have a different characteristics. And finally, you can find out the palette front. Palette front is our final goal to optimize our design. So this is a different point. And recently, we are requested to find out this palette front for this optimized design. And this is our system. Benson-san and Adam is working on this system. And so this is the conventional CFD flow. So you have a design, you have a CFD, and you got some result from CFD. And if you are not satisfied with this result, you need to go back to the design vector, and you can try the CFD. And now CFD is very, very useful and believable. You can do that, and you can reach to some result. However, if you have two more objectives, it's pretty difficult, extremely difficult to find out the best optimized parameter. So I added this part, and when you add this part, it's automatically searching the optimized system, and the computer to start to think and try to find out the optimized design itself. So this is a fully automatic optimization technique. And now we are developing this kind of code with JQuat people. So this is the inside. The combination of the parameter, I'm using the genetic algorithm. You know, genetic algorithm is based on the Darwin's evolutionary theory. And when this individual from first generation adapted to the environment, it survived and going to the second generation. So it's very, very simple algorithm. And we can easily to calculate and making a program of this genetic algorithm. For example, so when you are playing with blade, so blade characteristics, designs are based on the chord length and camber and the stack angles, and this kind of parameter can be changed to the digital line, something like this. So if you make this kind of parameter to the digital line, so this looks like a DNA, and this is the DNA from Papa, and this is DNA from Mama. So crossover is super easy. Just cut here and change both of them. And this is a child 1, and this is a child 2. So the information character from parents can easy to spread to the next generation. So crossover is super easy. And sometimes we need to think about the mutation. So mutation is also important function recovering from the local minimums. And mutation is easy. It's just randomly change the 1 to 0 and 0 to 1. So when you're playing with this kind of DNA line, genetic algorithm is easy and low cost of the calculation. The issue is the evaluation of the second generation. So in the second generation, this is a performance map and 2 objective function, and not all of them has good performance. Some of them are good performance. So when you think about the minimal problem, so this is a very, very good candidate. However, we also have a rank 2 individuals and rank 3 individuals. So we need to select these nice rank individuals and spread this information to the next generation. When you evaluate this kind of performances, how we can do that? Of course, we can do that by CFD, but CFD costs, for example, in my cases, it takes 2 or 3 hours using the 16 parallel computation and so on. And when you have a population of the something like 100, it's cost 10 times 100. And this is just our first next generation. And the important point of the genetic algorithm is a huge generation, you cannot find, the individual does not change so much. When you're looking at your parents, your grandfather, grandmother, your face is very similar. Not so many changes there. So when you're trying to optimize design, in my case, we are trying to do that 1,000 generation. It's cost too much. So when you're just doing the CFD, we cannot go to the 1,000 generation of the genetic algorithm. So now we need a meta model. Meta model means a surrogate model. So instead of CFD, we need to evaluate in somehow. In this case, I'm using the artificial neural networks. So as you know, artificial neural network is signal network in your brain. And this is the input layer, and this is the output layer, and this is the hidden layer. And if you have 3 more layers, you can say this is a deep learning system. And so each cells are connected each other, and this is mathematical models. And so this is cells and collecting the information with some certain amount of capillary load, and it's integrated this information. And if this cell body excited more than certain level, threshold level, it's passing out to this information to the next cell bodies. And you can combine this network, many cells and many networks and many coupling load. And you generate this network. So this is the input and this output. So the input is like a design of the blade, and the output is like efficiency. So this is an objective function. So when you have networks, and if you have a different input based on this neural network, this network will give you the new result of the efficiency. So we are trying to evaluate the performance of the different blade design objectives based on the different designs. So these neural networks can use instead of CFD. And this simulation cost is not so high. For example, when you trying the 1000 generation using these neural networks, it's running average computation cost is around 5 minutes or 6 minutes just for using the single computers. So the simulation cost is extremely low. This is also advantages. And this is the example of the optimization process. So this is the design vectors, and the vertical line is, again, it's an objective function. And so this is a real function, but nobody knows at the initial condition. So we are trying to change in the parameter, and we have some result based on the experiment or CFD. And so we found 4 point. And using this 4 point, our neural network trying to estimate, and must be this point is a minimum point. However, it's far from the real function, but it's okay. It's initial neural networks. It's not so clever, let's say. So it's a rough estimation at the initial condition. And we can confirm this condition. And so when you going to CFD or experiment, you have a validated result here. And in the next, we have 1, 2, 3, 4, and 5, one more point. And so we have an increased number of data, and then we can degenerate the neural network. So new approximation will have a better result. That means neural network getting better, getting clever, and it will give us the better result. So this kind of training using the good data is very important process. So when you understand this kind of work function of the neural network and genetic algorithm, you can see here, this is the loop for the genetic algorithm. And we are trying to do that 1000 generation. And so for the evaluation, we are using the neural networks. So it's very, very low cost. Around 5 or 6 minutes, we can finish it. But the first estimation is very rough. So after 1000 generation on the palette front, we can pick up some good candidate and confirm the CFD and increase the database and retrain the neural networks. And we can do that again, this genetic algorithm. So we have a better result. And again, we can confirm CFD and increase the database and retrain. So we need to repeat this kind of loop for the genetic algorithm and validation by CFD and retrain a neural network. We will have exactly optimized palette front. So this is the example of the optimization process, what I did it before. All of the data is coming from CFD, and the initial data is gray dot. And red dot is coming from the neural network assisted genetic algorithm. And so several loops of the neural net genetic algorithm. So we will have this kind of palette front clearly. So in this case, it's starting from the initial data and repeating the many process and retrain the neural networks. Finally, we have this kind of palette front. So it's very, very powerful for the automatic searching system. And the most difficult point is the design. So especially for the blade design, it's complicated. And but when you keeping this function, so our d theta is dm tangent beta. It's very simple equation, but when you keeping this relationship between the meridional axis and the radial axis and the streamline, so you can generate three-dimensional curve easily. And one more unique point of our system is when you're playing with this smooth design variables, so this is a blade angle from leading edge to trailing edge. Normally, when you are playing with a CAD, it's requested more than 100 points. Otherwise, it's very difficult to get a smooth curve. So, however, when you're playing with the 100 point just for the blade angle, it's not a good idea. So I using the Bezier curve and just 1, 2, 3, 4, 5 control points are requested to generate this smooth curve. So that means I just can play with this 5 control point and we have a very smooth curve and we can generate a nice blade design. Just 5 control points. So this is also unique techniques. So it's time, and I want to finish my presentation. So I introduced the optimizer, and it's based on the genetic algorithm, and the neural network is used for the meta models. And it's very, very useful for the design of this kind of complicated design. And previously, nobody knows how to design of that. But when you're using this optimizer, you can design any kind of turbo machinery. And moreover, for the renewable energy, the boundary condition is always changing. So that means there's no rated speed, rated condition of the flow. So we need to maximize the integrated value from the energy resources. So it should be operated under the off-design condition and maximum speed and so on. So it's multi-point objectives. For this purpose, this design technique is very, very useful. And for the renewable energy, turbo machinery is always combined with the turbine and pumps and so on. So it's required the very wide range, operating range, and this design technique is very, very useful. And lastly, I just introduced my photo from our student, and Benson enjoyed with my student, and Adam and me, and Benson went to the field of the wind turbine, and Dr. Anthony, James, Patrick, they came to our lab and stayed very, very shortly, but we enjoyed a lot about the collaboration. And Mrs. Grace just arrived, and she's a PhD candidate, and I'm very, very happy to work with her. Thank you very much for listening my presentation, and if you have a question, I'm very happy. Thank you.
Yeah, thank you very much, Professor Sakaguchi, for such an informative presentation. Maybe we can give a nice clap to Prof for such a... Yes, so at this time, I would like to request, maybe we have 2 or 3 questions that we can ask to Prof about the presentation. Okay.
Thank you, Prof, for the good work and the optimization problem that you have demonstrated to us. A very nice keynote speech, and also thank you for the students, staff members of JKUAT that are training in your laboratory, and also the work that you are doing with our team from JKUAT. We appreciate your support. Maybe a clarification I wanted to find out from you. In this setup of the turbo machinery or turbine, which, in your opinion, is the best orientation of the axis of the turbine that generates the best energy and maybe more efficient? Has research focused on the various orientations of the axis of the turbine? Thank you.
Much. So now I explained just the optimization of the turbo machinery, and so it's of course it's adapted for the renewable energy, and this kind of technique is also can use the maximize the energy and the combination of the energy resources. So optimization problem is everywhere. And for example, the energy from the wind, energy from the geothermal, energy from the turbine, wind turbine, and so on. So it's always changing under the various changing of the boundary condition. So we need to optimize this kind of energy mixing. So it's also useful, this kind of techniques. So I just explained as a turbo machinery design. It's useful, but I need to say when you're thinking of the energy mixing, it's also useful. Of course, and if you are playing with the farm layout, so farm layout is also useful design technique. So when you have several types of the wind turbine, and if you have a huge scale, you can install the many turbine there, and how to making a layout avoiding from the wakes. So it's also interesting topics and challenge. Now we are trying to start the farm layout optimization. So, I mean, there are many there are an objective target there, and we can use the similar technique to the design of the field. Thank you.
Okay, so thank you so much for your nice presentation, and so this is very interesting for me. So my question is the optimization scheme. So your optimization scheme is based on the steady state CFD results, but in a real world, so that includes the transition phenomena. And my first question is how about the effect of the transient phenomena on your optimization schemes?
Find out there where is the most interesting point of program activity measure. So this is another it's possible.
Okay, thank you. And the second question is, so I think that is the understood, I think. But so how about is the potential or possibility of variable geometrical turbine systems in the tidal power generation system?
So this is a simple variable geometry system for the turbocharger. This is the inlet guide band for the turbine of the turbocharger. So this inlet node changing the direction always. So we optimize this angle and shape of the blade and position of the blade. So it's also an interesting target. And if you have many variables, it's a good chance to optimize the geometries. Thank you.
Okay, thank you.
Thank you very much for such a interactive session. I don't know if we have any burning question from the participants. Just one, because of time. If there is none, then I hand over the mic to Dr. John Odhiambo to conduct the remaining session as we wind up.
Thank you very much, Dr. Benson Oyunge, for spearheading this session. And thank you very much, Professor Sakaguchi. So I would like to request our Principal College of Engineering and Technology, Professor Engineer Hiram Nderitu, to come forward to present to us a small gift that we prepared for our guest speaker. So, Professor, please come over. And Howie, please. Yeah, okay, thank you, Prof. We have a small, we should take a photo of our media team, please. It's ready. And, let's clap. Let's clap for Professor Sakaguchi and our principal, Professor Hiram Nderitu. Yeah, thank you very much, Prof, for the wonderful job that you've been doing and accepting to be our keynote speaker. Thank you very much. Thank you very much. As they exit the stage, let's continue to give them a round of applause. Yeah, let's continue to give them a round of applause. Exit the stage. Yeah. Okay. Yeah. Thank you very much. Yeah. One more round of applause for Prof. Okay, thank you. Now we are going to the next order of events. We've taken a little of time. Now we will have a tea break. I request that we take our tea very fast and the snacks that are available. And if possible, and if we have Dr. Macharia and also Dr. Florence Kiburi, please make sure that the first session, which will be headed by Robert Macharia, I think will remain in this hall, and then the next session that will be headed by chaired by Dr. Engineer Florence Kiburi should go to the next room, the breakaway session. And I request that we do that. We take our breakfast just 20 minutes instead of 30, or maybe it should be 18 minutes, so that by 10:10, we convene back for the session 1 and session 2. So session 1 will be here and session 2 will be in the next room. And I request the session chairs, session 1 and session 2, to help us so that we are able to recover the 10 minutes that we shall have lost. So if there isn't anything from the organizers, I request that we go for our tea now. Thank you very much, and let's convene back in the next 20 minutes. Oh, just a moment. One more thing is that those who are having presentations in session 1 and session 2, please send your session 1. Please send your PPT to A Kiva, akiivaa@jquat.ac.ke. Send your presentations to akiivaa@jquat.ac.ke. Thank you.